Hi everyone, today we're going to talk about the surface area of composite figures. Now remember that a composite figure, which we've talked about in 2 dimensions, but today we're going to talk about in 3 dimensions. A composite figure is a figure that can be decomposed or deconstructed or broken apart into different 3D figures. So there are 3 steps to follow. First, you need to determine the 3D figures you can break the composite figure into. So they're going to be your basic 3D figures. Some of them will be polyhedrons like prisms or pyramids. Some of them will be cylinders or cones. So figure out what 3D figures you can break the composite figure into. Find the surface area of each figure. And then step 3, subtract out any unnecessary parts of the figure. So sometimes when you add the total surface area of 2 different figures, but they come together to make a composite figure, sometimes you have some overlapping parts that you need to take out. So subtract out any unnecessary parts of the figure. Now we have example 1A, 1B, and 1C today. They all say find the surface area of the following composite figure, and they start out with 2 questions before you actually do the computations. So the first question is, what 3D figures can you break this into? Well, I've got kind of like a box down here and then another smaller box kind of laying on top. So the 3D figures we can break this into would be prisms. There are 2 of them, and they are rectangular because their bases are rectangles. So 2 rectangular prisms. 1 small, 1 big. Now what needs to be subtracted out? Now this is where it would be helpful to be able to actually hold this figure in your hands, turn it around, open it up, see what it's made of. And so what I've done today is I've kind of zoomed out my camera more than usual because I've made some models of our figures. So here is a ballpoint pen box and a tape box, and it kind of came together nicely to make the figure, the composite figure that you see here. Now I do have a large prism, large rectangular prism, and a smaller rectangular prism. I can kind of remove them, so that's helpful. But I need to know what needs to be subtracted out. So if I find the total surface area of the big prism and the small prism, I need to know what needs to be taken out so that only the surfaces are covered. So I notice that if I pull this tape box off, I've got this extra surface right here that really needs to come off. And in addition to that, I've got this surface down here that needs to come off because I really don't want any surfaces on the inside of the figure. Okay, that's not surface area, that's area inside of the figure, and that's not okay. So I need to take those off. So what I would do is I would remove this bottom right here. So I would remove that so it's nice and open. Set that to the side. And then I would also remove this piece right here. And notice that it's not the big base. It's not the base of the larger prism. It's actually equal to the base area of the smaller prism. So I need to take this out as well. It's going to be difficult. There we go. So I've taken out 2 bases, and they happen to be exactly the same shape, and they also happen to be the area of the base of the smaller prism. So I'm going to take these out, and now whenever I put my composite figure back together, I've got this empty space, and when I put it one on top of the other, now there's no area that's on the inside. Right? So what I need to do is I need to find the area of the surface area of the larger prism, the smaller prism, and then I need to subtract out 2 of the smaller base areas. So that's what I'm going to subtract out. So this is kind of our model of what it is that we're doing, what it is that we're finding. So we have 2 rectangular prisms. We need to subtract out 2 small rectangular bases. And now we kind of can put together our plan. So we want to add together the total surface area of the large prism and the small prism, and then we want to subtract out 2 small rectangular bases. So let's create our plan. We need to take the surface area of the big prism, add to it the surface area of the small prism, and subtract from it 2 bases of the small prism. So that's kind of my plan. So I determined the 3D figures that I could break the composite figure into. I'm going to need to find the surface areas, and then I know what to subtract out. These are the unnecessary parts of the figure. These 2 little bases right here, that was on the inside, and I needed to take those out. So now I need to actually use my formulas for the surface areas. So the surface area of a prism is the perimeter of the base times the height, plus 2 times the area of the base. Same thing for the small prism. The perimeter of the small base times the height of the small prism, plus 2 times the area of the small base. And then I subtract out 2 bases from the small prism. Now here's kind of my layout, my plan, and then all of my formulas in it. But I kind of noticed that this is the perimeter of the small base times the height of the small prism, plus 2 times the perimeter, 2 times the area of the small base. But then I'm subtracting 2 times the area of the small base. So this right here can kind of get canceled out, right? It doesn't get canceled out with this because this is 2 times the area of the big base, but this is the small base and this is the small base. So if I add 2 of them and then subtract 2 of them, well, I net 0 of them. And so I can kind of recreate my formula, or the surface area of the big prism plus just this, which happens to be the lateral area of the small prism. So that's an alternate form of my plan that could work because it means the same thing. So I'm going to go ahead and work on this. I need the perimeter of the big base, so that's 12 plus 5, which is 17, and then plus another 12 plus 5, so another 17. When I add those together, I get 34, times the height of the large prism. Well, the height of the large prism is 4 feet. Plus 2 times the area of the big base. Well, the area of this big base down here is base times height, so 12 times 5, which is 60. I want to add to it now from the small prism the perimeter of the small prism's base. So this would be, if this is 8, then this right here is the same distance as right here. This is 5. So that's 13, and then another 8 and 5, that's another 13. So 13 plus 13 is 26, times the height of the small prism, that's 2. And then I can add 2 times the area of the base, so 8 times 5, which is 40. So I can add 2 times 40 and then subtract 2 times 40, but we already realized that that kind of cancels itself out, so it's unnecessary. So I'm going to continue with my plan. 34 times 4 is 136. 2 times 60 is 120. 26 times 2 is 52. 136 plus 120 is 256. And then plus another 52. That's 308 square feet. And that's my total surface area of the composite figure. So I was able to identify what my composite figure was made of. I subtracted out 2 small rectangular bases based on the model that I made. I came up with a plan. I inserted the formulas into the plan. I was able to see that the plan can kind of be simplified. And that way, whenever I inserted my dimensions, I had a much simpler way to find the total surface area of the composite figure. So let's look at example 1b. And example 1b is missing something, so I need you to draw, like it looks like there's no walls for this interior part, so I need you to draw some walls here. Probably should have made it dashed. I think that would look better, but that's okay. So I need you to draw some walls there. So in this figure, this composite figure, what 3D figures can you break this into? Well, the large figure looks like a really big disc, like a flat cylinder. And then the inside, what's kind of been taken out volume-wise, is a smaller cylinder. So the 3D figures you can break this into would be 2 cylinders. A small one and a large one. Now, what needs to be subtracted out? Remember, we're finding surface area. So we're finding the area of all of the surfaces on the outside of the figure. And so when you think about the large cylinder and the smaller cylinder and taking the cylinder out, you can be removing volume, but what you might be doing is also adding some surface. So you might be adding some surface area. So let's look at kind of a model of what this might be in real life. And to me, it kind of looks like a roll of tape. Maybe not a roll of duct tape, but that's what I had on hand. So this is what I have. I have a roll of duct tape. And so what I'd like to do is I'd like to cover the surface of this duct tape with paper. And in order to do that, I created 2 cylinders. So I'm going to go ahead and cover this on the outside. So if I cover this on the outside, I need, for my bigger cylinder, I need lateral area, right? Lateral area. I also need a base on the top and another base on the bottom. Okay, so I have a cylinder that has lateral area and 2 bases, right? So that's what I have. And it's made of paper, so it's kind of flimsy, so don't judge. But we have a large cylinder. Now inside, we should also have a smaller cylinder. So I'm going to remove this so I can actually put a cylinder inside. Inside, I have a smaller cylinder. Okay, lateral area, 2 bases, kind of inserting it inside. Not as easy as it looks. Let's try it from the other way. Move these pieces around. Okay. Much easier. Good grief. Okay, there we go. So the inside, we've got the lateral area, we have a base, and then we have another base, right? So we've got that cylinder inside of the larger cylinder. So I'm going to go ahead and cover this up like it should have been. Here is my tape, right? It's all been enclosed. But what I want is just the surface area of the roll of tape. So there are things that need to be subtracted out. For example, in this base right here, I really need to take out this circle, right? I need to take it out. So I'm going to go ahead and remove that. And unfortunately, underneath, there's another circle from the smaller cylinder. So I need to take that out as well. Okay. So now I've got much more closely resembling what I want, right? But I need to flip this over and I need to do the same thing to the other side because I only want to cover the roll of tape itself. I don't want to cover this hole on the inside. So I'm going to turn this over. I'm not going to forget my base. Okay. So I need to, again, remove this circle, right? So I'm going to go ahead and remove that circle. Okay. And then it turns out that in order to get to the inside, I've got another circle underneath from the smaller cylinder. So I'm going to remove that also. So now I have stuff that's falling apart, but now I have everything covered, right? The inside is covered in orange, the outside is covered in green, everything is covered. And that's exactly what I wanted. I want to find the area of all of these surfaces. So we can add the surface area of both cylinders, but then we've got to subtract out some stuff. So I'm going to move this aside, and I'm going to show you all of the pieces that we subtracted out. Let me move that to the side. We subtracted out 2 circles like this, and we subtracted out two circles like this. So if I put them all on top of each other, notice that they're all the same size, right? They're all the size of the base of the small cylinder. And so how many were there? 1, 2, 3, 4. There were 4 of them. And so what needs to be subtracted out is 4 small circular bases. I need to subtract out 4 small circular bases so that I can get the surface area of this figure. Because I want all of the surfaces covered, but I don't want anything enclosed. So I had to take out 2 small circular bases from the small cylinder, and then I had to cut out those green parts, those green circles, from the bases of the larger cylinder. So 4 small circular bases in total came out. So my formula, my plan, if you will, is the surface area of the big cylinder plus the surface area of the small cylinder, and then minus 4 circular bases, from the small cylinder. So that's my plan, right? So let's go ahead and insert the formulas for the surface area of these cylinders. So for the surface area of a cylinder, we have the lateral area, 2 pi RH, plus 2 bases. So, 2 pi r squared. That's a 2. And then I need to add to it the surface area of the smaller cylinder. So that would be another 2 pi RH plus 2 pi r squared. Now remember, these are different. The surface area of the big cylinder and the small cylinder are going to be different because the radius and the height are different. So I guess here the height would be the same. So the height of the large cylinder is 3 meters and the height of the small cylinder is 3 meters. So that's the height for both of them. But the radius is different. So the small cylinder, the radius is 5 meters. For the large cylinder, the radius is 9 meters. So these r's are not the same thing, which means that we're not going to have a number here and a number here that's exactly the same. They're going to be different. And I need to subtract out 4 small bases, and a base is a circle, so pi r squared. This is the small radius. Now at this point, the small radius appears here and here and here. And these terms are similar. I have 2 of them, and then I subtract 4 of them. So really, I'm netting minus 2 of these terms. So if you want, you can recreate this formula to be the surface area of the big cylinder plus the lateral area of the small cylinder, and then minus 2 bases of the small cylinder. So if you want to rewrite your plan like that, that's totally fine. So let's go ahead and put some pieces in the right place. 2 times pi times the big radius, which is 9 meters, times the height, which is 3 meters, plus 2 times pi times the radius of the big cylinder squared, so 9 squared, plus 2 times pi, now we're on the small cylinder, times the radius of the small cylinder, which is 5 meters, times the height, which is still 3 meters, plus, we could add 2 and then subtract 4 of these terms, or we could just net a minus 2 of them. So I'm going to do that because 2 pi r squared minus 4 pi r squared is minus 2 pi r squared. That's combining your like terms. So I'm going to do that. So now whenever I put these together, 9 times 3 is 27. 27 times 2 is 54 pi. Plus 9 squared is 81. 81 times 2 is 162 pi. Plus 5 times 3 is 15 times 2 is 30 pi. And then 5 squared is 25. 25 times 2 is 50, so minus 50 pi. Okay. So I'm going to combine my like terms. I'm actually going to do 54 pi minus 50 pi, which is 4 pi, plus 162 pi, so that's 166 pi, plus 30 pi, that's 196 pi. And we're measured in meters squared. This is the total surface area of the composite figure. So we had 2 cylinders. We needed to subtract out 4 small circular bases. We wrote our plan. We inserted the formulas into our plan. We noticed that this could be combined to make minus 2 pi r squareds, so we could rewrite our plan a little bit if we wanted to. And then we inserted all of our dimensions. We used PEMDAS to get our answer of 196 pi meters squared. Okay, so up until now I've had kind of examples to help us. We had the tape, we had the boxes. In example C, it's all visual. And so I'm going to go ahead and move this down a little bit so that you can see the work a little bit better. What 3D figures can you break this into, and what needs to be subtracted out? So what I'd like for you to do is pause your video, write the 3D figures you can break this into, write what needs to be subtracted out, and try to create a plan. So get that far. Pause your video. So perhaps you identified the 2 figures as a rectangular prism and a rectangular pyramid. Now if you look closely, it's not wrong, but if you look closely, this base is 12 feet by 12 feet. So not only is this a rectangular prism, but we could also go so far as to call it a square prism. And this pyramid also has a base of 12 feet by 12 feet. So not only is it a rectangular pyramid, but we can go so far as to call it a square pyramid. Now what needs to be subtracted out? Well, we need this square right here taken out of the prism. And then we also need the base of the pyramid taken out so that you can get to the interior surface of the pyramid. So we need to subtract out 2 rectangular bases. We could also say 2 square bases because they're rectangles, but specifically they are squares. So your plan should be to take the surface area of the prism, add the surface area of the pyramid, and then subtract 2 bases. So let's fill in the formula for our plan. So the surface area of a prism is the perimeter of the base times the height plus 2 times the area of the base. And then we add to it the surface area of a of a pyramid. So that formula we talked about the other day is 1/2 the perimeter of the base times the slant height plus 1 area of the base. Notice that the bases are the same. So the base of the pyramid is this square, and the bases of the prism is also that square. So I'm going to subtract 2 areas of the squares. Now, the perimeter here and the perimeter here are both the perimeter of the bases, and if the bases are the same, then the p's are the same number. The height is of the prism, and these bases are all the square bases. They're all the same thing. So if here I add 2 bases and here I subtract 2 bases, well, that's going to net just the plus 1 base. So we can change this plan or rewrite it to be just the surface area of the prism, the lateral area of the prism, plus the full surface area of the pyramid. So you could simplify your plan to look like that. Okay, so let's insert some of these pieces. So the perimeter is 12 plus 12, which is 24, plus another 12 plus 12, which is 48. The height of the prism is 15. I'm not going to add 2 area of the bases because I subtracted 2 area of the bases here, so I'm just going to move on to plus 1/2 times the perimeter of the base. Well, remember the perimeter of the base was that perimeter of the square, that was 48. Times the slant height, we do not know that yet, and then plus the area of the base. Well, to find the area of a square, you take a side and you square it. So 12 squared is 144. Now the difficult part is trying to find that script L, that's slant height. And so I'm going to take this square pyramid and I'm going to redraw it so that we have a better idea of what this looks like. So I've got this pyramid here. Looks good. And then I know that these are squares, or sorry, these are right angles. Here's the center of the square. Here's the height, which I know that the height of this upside down kind of inverted pyramid is the same thing as the height of the prism, right? So this has to be 15. But what I'm interested in is this slant height right here. And that slant height is going to be at a right angle on the lateral face. And then I'm going to have this distance right here as well. Now, you'll notice that this height of the pyramid is at a right angle to the base always, because that's the way the height is. And then remember that this distance is 12 feet. So this distance right here must be half of it. It must be 6 feet. So what I have is a nice right triangle here, with side lengths of 15, 6, and then some slant height for the hypotenuse. And we know that we can use Pythagorean theorem to find the missing side length of a right triangle if we have the other two side lengths. So 15 squared plus 6 squared equals the slant height squared. That's 225 plus 36 equals the slant height squared. If I add those two, let me see if I can get this clearer. There we go. If I add those two together, I get, what is that, 261. If I square root both sides, I get L equals the square root of 261. 2 plus 6 plus 1 is 9. That's divisible by 3. So I know I can break this into something that is 3 times something else. The rule is that if the sum of the digits is divisible by 3, then the number itself is divisible by 3. So 3 goes into 26 8 times with a remainder of 2, and 3 goes into 21 7 times. 8 plus 7 is 15, so that's also divisible by 3. So 3 times 3 times 3 goes into 8 2 times with a remainder of 2, and 3 goes into 27 9 times. So this is 9 times 29. That's 3 square roots of 29. That's the simplified version of this radical. So that's my slant height. This is 3 square roots of 29. So now I need to go ahead and put everything where it belongs. 48 times 15 is 720. Half of 48 is 24. 24 times 3 is 72 with the square root of 29. And then plus 144. Now I can't add this term with these two, but I can add these two together because they're just constants that are not in a radical form. So if I add these together, the surface area of the total composite figure is 720 plus 144, which is 864, plus 72 square roots of 29, because I can't combine those, they're not like terms. And I'm measuring this in feet squared. So there is a nice set of 3 examples of how to find the surface area of composite figures. If you feel like you need help visualizing, it's always a great idea to find things around the house, or things around the classroom in my case. So you can always put them together and try and find the surface area of what it is that you have for your problem. Sometimes you don't need it, but when you're first starting out, it's okay to go find those examples.